Thank you. All right.
Okay, hi everyone. Today I'd like to tell you a little bit about AO, which is a sort of actor-oriented machine that we built on top of Arweave, which is a permanent hard drive. We started 7-8 years ago building, basically, we saw the idea of on-chain storage and thought that was really cool. As a ledger of history and culture and information generally, yeah, we thought that it would be exciting if we could make that scale, because at the time you could do this with Bitcoin. People, in fact, actually Satoshi right at the beginning was embedding in the first block of Bitcoin a record of history in some sense, a newspaper headline. But when we started, there was just no way to make it so that you could fit large amounts of data in there, and it just seemed like an obvious use of blockchain technology and a good use of censorship resistance to provide a permanent neutral hard drive for anyone to use at minimum viable cost. Then somewhere along the line, I think it was about 2020, we realized that, well, there's this notion of lazy evaluation of computation that comes from functional programming, where basically you can queue up a set of inputs to a computation, and only when you require the output do you actually trigger the computation itself. And we thought this was pretty interesting. People were already using Arweave to build decentralized web applications, this type of thing. But it would have been really useful if they could do smart contracts on top of it. And well, it was a pandemic and everyone was like locked indoors. So we hacked together like a 150-line JavaScript implementation of what we called SmartWeave at the time, which was basically an MVP of lazy evaluation of smart contracts. And at the time, it was really only us and Celestia, who were at the time called Lazy Ledger, who seemed to think this was an interesting or viable route for smart contracts. But through the process of building out that MVP and seeing people adopt it and start to put it to use for things, we realized actually maybe there's something pretty useful there. And over time, that sort of developed, and there was a small ecosystem of people building these smart contracts. And they started to use what are called bundled data items in Arweave. Essentially, Arweave doesn't care about giving you a data availability proof. What it cares about is actually a long-term availability proof. So if you upload a piece of data to Arweave and you pay for it and you seed it, then it will store your data for an arbitrarily long period of time according to an economic model that is transparent and verifiable. But if you add there something that can give you a data availability proof, and given that Arweave scales to like the max transaction size is 2 to the power 256 bytes per transaction, so it's like excessively large, then you have a substrate upon which you can put the inputs and the initial state to a smart contract such that the output state can be regenerated. And about 18 months ago now, we were working on a project to bring Odyssey, which is a sort of, I was about to say decentralized social media platform. That's not true. It marketed itself as a decentralized social media platform, and it got about 7-8 million monthly active users who were all really engaged, and you would say passionate about the idea of decentralization, but poorly served by the technology. So we were helping them actually properly decentralize the system, and we needed a smart contracting engine that would scale to support 7-8 million monthly active users. And we were looking at the landscape, and there's just really nothing that could do that viably. So we started thinking about SmartWeave again and built out what became AO, which is fundamentally just a hyperparallel computer. So the A and the O stands for actor-oriented. Before starting Arweave, I was doing a PhD in distributed operating system design, and I spent many years building operating systems with this programming language called Erlang, which had the same sort of primitive idea of, well, instead of sharing state between different processes in the system and having them lock in order to access and mutate the state, basically, why don't you instead have them be fully asynchronous, then have a sort of, you could say like commoditized set of, they call them schedulers, but they're essentially execution units, I suppose you could say, under the hood that, just pick up these processes which are represented in an extremely lightweight way. Green threads, if you're from the operating system world. There we go, I got one nod. Yeah, they're green threads, so they're extremely lightweight. You can have millions of them inside a single box, and then they just pass only the state that is needed to affect the other processes, and they have no global locking mechanism. And we thought that, well, you layer that with SmartWeave and its lazy evaluation system and put that on top of Arweave, and there you go, you end up with something that approximates a world computer. Yeah, any number of processes running in parallel and only coordinating when needed. So it applies, the actor-oriented model really has no notion of global shared state at all, other than Arweave, which writes its history of interactions on a process, such that anyone in the future can come along and reevaluate them and check the validity of the outputs that were given and use them in another computation, perhaps. Instead of enforcing a single shared security model, we thought that that doesn't really make sense. Like, the use case that we wanted to support was people being able to trade the real world, like legally enforceable rights associated with content. So when they upload a piece of data to Odyssey, they should be able to, well, for a start, own those rights themselves, then trade pieces of it. So tokenize in a fungible fashion the royalty stream created by the content. Now, you don't need Bitcoin level, security to make that work. Like, it really isn't necessary, and it does necessarily come with cost. Getting 10,000 nodes in the world to perform every state transition is just a costly endeavor. If it's a 5-cent transaction, that's not appropriate or necessary. So instead, and we looked at like the security model from the ground up, and we realized that really what you need is the recipient of a message. So someone that's receiving a small piece of the state of another process needs to be able to trust it to some degree. And in the ideal case, and this is the design we ended up with, they should be able to specify that at runtime. So you try and send a message, and they say, okay, I think the maximum economic damage that that message could do if it were fraudulent is $100. So I will ask for $10,000 of singly assigned stake for a period of 7 days as a fraud detection window. And then, well, for a start, you've disincentivized fraud, but you also get a remediation system, essentially. So, okay, fraud happened, you can detect it, you can share some of that $10,000 that you put aside with the person that detected the fraud in the first place, and then you also have capital with which you can remediate the fraud. And so if you put this all together, you end up with a system where the processes are all interoperable. They're all running the same standard, and they can interact as if they are essentially part of the same, what we call single system image, which is an idea from distributed operating systems in the 70s. Basically, you have many pieces of hardware, but from the user's perspective, when you deploy on top of it, it looks and feels like you're using one giant machine. Well, that's what AO gives you, except you can plug in as much hardware as you want, and you can have different security requirements in the appropriate places in the system. So in order to glue all of this together, actually, we, I guess, launched the public testnet of AO probably a year ago today, at ETH Denver, in fact. And people started picking it up and using it very quickly, and it was a testnet, and it ended up carrying tens of millions of dollars of value, which is not something I would recommend, nor is it what we planned, but it was safe in the end, but still, there was a very rapid adoption of it that led to about 1.5 billion messages being transferred. By the end, it was running at, the testnet was at like 300, 400 transactions from users per second. On a busy day, at least over 100 at any given point in time. So it was very well used, but in a different part of the world, at exactly the same time, the HTTP message signatures spec was formalized. And with AO, what we were trying to do was really make it so that there's a smart contracting system that's available in the most neutral form, the most neutral language, if you will, possible. And we've always known that Arweave data items, they look very much like HTTP responses. And actually, an Arweave node, right from the beginning, was just a HTTP server. everything spoke HTTP so that you could throw a browser at a node and have it render a web page for you. And that's how, like the first use of the system was to be an archive of the internet that ran parallel to the internet. So it's very helpful if you can then, when you've uploaded a page, go to that transaction ID and have it render in the browser. But that also meant that we ended up with a system where you have something that looks very much like headers, basically headers in a body, which almost exactly maps onto HTTP itself. But what was missing was signatures. We added our own signature form, and subsequently it wasn't really like a normal HTTP response. And yeah, the idea, I guess, like lay dormant for a few years. But this time last year, the HTTP message signatures standard was ratified. And that gave now a mechanism by which you can get repudiable responses from web servers. So my sense is that the use case they intended this for is more niche than the one I think will actually end up being used for. I guess just like HTTP itself. It was originally like a phone book for CERN. Everyone can have their own HTTP server running a little web page so that they could get each other's phone numbers. And then it ended up being like the dominant application platform of the planet. It's kind of crazy. Anyway, we think it'll be a similar story here. So this provides a good substrate. And when we looked at, okay, well, how would we deploy this in practice? We realized what we really needed was a generic representation of blockchain-like computation and interactions, and subsequently a way to link particular spots in the program state space with outputs. And we did that by making this system we call hash paths. So you ask two different nodes for the same set of computation. That's basically I take message A as my base, and I apply message B to it, message C, and so on, basically as a sort of I won't get into the math of it, but it's a form of singleton, essentially. You have the representation of the program as a single atomic unit, and then you apply a request on top of it. You get another response, which itself can take further requests. It's a very simple grammar, I guess. It's like it represents that local state per process. And so you can create these hash paths along the path of scheduled interactions on a process. So you say I have message A, stroke message B, stroke message C, stroke message D, and you end up with a Merkelized list, or rather a Merkel state root that represents that in a single identifier. And then, of course, you can get multiple parties to attest to the data that is found at that position in the state space for that program. And you can merge those signatures together. You can also do so, and this is a nice thing about the spec, using different signature algorithms. So you could have a RSA SHA-512, I think was the default one that they have in the 9421 spec. You could have it work that way if you wanted to, but you could also have ECDSA and potentially many other forms of attestation of correctness, even ZK proofs if you want. And the one that we went to market with, we launched mainnet a couple of weeks ago, is just normal signatures, but TEE attestations on top of them about the correctness of the output. And then you can stack those across a TEE from AMD and a TEE from Intel soon, not quite yet, but yeah, in a few weeks we think. And then you get a robust attestation of the state of the program at a specific point. And that gives you something that's really, I think, pretty interesting and unexplored, which is that instead of having a traditional consensus mechanism whereby, or at least enforcing a traditional consensus mechanism, you can use one if you want, but instead of having one of the default layer, the base layer, you pass around these Merkle paths. So let's say an output of one process contains a message that you want to pass to another process. Well, there's a Merkle, it is a Merkle root, but there's a hash path for that output that you're putting into the input of another process. And so you end up with a tree like this, where the Merkle roots are getting merged over time. And so here we have, let's say, like 4 different Yeah, it says bank there, but we could say that's like a token processor or something of the same type. When they pass messages between each other, they're taking small proofs, or yeah, not really proofs, Merkle roots, from which proofs can be derived, and passing them down the chain. And there's no additional consensus required here. That's just the single message that needs to be sent in the system in order for anything to coordinate or achieve, anything in a distributed system. Oh, 2 minutes. All right, I'm definitely going to run out of time. But what you can do is you can set the hash path acceptance rules on the other side to say, okay, I'm only going to build upon or accept a hash path that, for example, had a ZK proof. And what you do if you do this at scale is you get like a gradual consensus about the outputs of the state transitions in different processes in the system. And that gives you, through really like unorthodox means, I would say, a like slow, approximate, or it gives you a mechanism by which you get a proof of correctness of most of the outputs of the system at any one point in time without having any additional like blockchain type communication overhead. It's big O1 communication overhead. It's very, very novel and interesting, I think. And we left it open so that that hash path algorithm can be outfitted whichever way you want. And all of this is expressed inside basic HTTP semantics. It's like the most neutral representation of a blockchain we could come up with. And it gives you another feature, and I guess I'll stop here, that we think is particularly interesting, which is that you, in a traditional blockchain network, if you really think about it, the trust that you're having to accept as a user doesn't end with the blockchain. Almost all of the time, virtually no one is running their own nodes. Like infinitesimally small proportions of the industry. Out of interest, who here runs their own Ethereum node when they interact with Ethereum? We got like 130%. Okay, a very, very, very small number of people. And what's interesting about this mechanism is that because it's all expressed in HTTP, that call to what would otherwise be an RPC server is actually just another call to the network. And so that state transformation that you want in order to get the output, the indexed output that you need to show you your balance inside the network is in fact part of the network itself. There is no differentiation. The edges go right to the user's browser. All right, and I'll leave it there. But thanks, everyone.